For the first century of the automobile, whenever a crash happened, the blame almost always fell into one of two categories. The human behind the wheel made a mistake, or a physical part of the machine broke down. But self-driving cars present an entirely different problem. Engineers can build a vehicle with hardware that functions flawlessly, where the brakes actuate perfectly and the cameras operate exactly as designed, and a crash can still occur. The danger now often comes from the environment itself. A sudden plunge into a dark tunnel or blinding sun glare reflecting off a wet road can push otherwise perfect sensors past their operational boundaries. In the safety framework known as SOTIF, safety of the intended functionality, this specific type of hazard is categorized as Area 2. These are the danger zones we already know exist, and we know they pose a high risk to the system. Modern engineering now focuses on the control of these known external variables. Success is measured by how effectively we manage the risks we have already identified. Self-driving relies on a loop: sense, plan, and act. Vulnerabilities start in the sense phase. A bridge's steel cables can confuse radar, generating ghost targets. Fed into the plan phase, the system scrambles to calculate a safe trajectory based on an inaccurate environment. Clause 10 of the SOTIF standard dictates exactly how engineers must handle these cognitive gaps. They are required to take every known weakness and intentionally expose the driving logic to millions of grueling simulated edge cases. This massive scale of simulation acts as a digital mapping tool. It traces the exact edges of what the car's perception system can and cannot handle across thousands of weather patterns and road layouts. Aggressively mapping these limits serves as an admission that no artificial intelligence is omniscient. If we know the system will eventually encounter something it cannot process, designing a reliable fail-safe becomes the most critical task in the vehicle's development. So what exactly must a multi-ton vehicle do in the fraction of a second it realizes it no longer understands the road ahead? The answer is a programmed mechanism called a fallback. Instead of guessing its next move based on bad data, the system gracefully surrenders control. The ultimate goal of this fallback is reaching what engineers call a minimum risk condition. The car must navigate itself away from active traffic and transition into a safe, completely static state. Executing that maneuver is incredibly complex. The vehicle has to calculate a stopping position that won't suddenly disrupt the flow of traffic behind it or trigger a secondary collision while trying to pull over. Self-driving technology reaches its highest utility when it accurately identifies its own limits, signaling exactly when and how to give up control safely. Even with millions of miles of perfect simulations and highly refined fallback maneuvers, deploying these vehicles into the real world means accepting that a baseline of residual risk will always remain. This brings up the final ethical test of Clause 10, determining if the risk left over is actually acceptable to society. We cannot evaluate safety simply by looking at global averages. A system that successfully navigates 99% of its miles can still hide devastating, hyper-localized failures. Consider a vehicle that performs perfectly on open highways, but consistently fails to detect pedestrians crossing at one specific, highly complex city intersection. This introduces the standard's concept of local integrity. The remaining risk cannot be disproportionately concentrated on specific geographic locations or placed onto vulnerable groups of people. Subjecting a vehicle to these known scenarios is a verifiable promise to the public. It proves the manufacturer isn't just releasing software and hoping for the best. Adhering to these local safety requirements allows manufacturers to move past global averages, creating a system that remains reliable even in the most demanding environments.